Welcome to video 14 from Superquiz 1. This is the final problem on the Superquiz, and we are asked to compute local extrema. So here we're given a slightly more complicated function of two variables than in the last several problems, and we want to determine whether or not the following statements are true. So things like where does f have a local maximum or minimum or possibly saddle point, or how many critical points it has. So let's just go through the normal process. So in order to find local extrema, we know we want to find the critical points of the function. The critical points are going to be where the gradient is going to be 0 or doesn't exist. So let's see here. So we want to know where we want critical points. So critical points occur where the gradient is equal to 0 or the gradient does not exist. Now, this second condition is not going to be terribly relevant here because we're looking at a polynomial. The gradient is going to exist everywhere, right? This is a beautiful, everywhere differentiable function. So there's not going to be an issue with that. So we don't need to worry about this. So don't worry here. Okay, so we're mostly going to be interested in where is the gradient equal to 0. Well, we better compute the gradient. So the gradient of f is going to be, well, we need to take the partial with respect to x. So remember, that means we're going to treat all the y's as constants, just like a 3. Let's see, there's another constant, hey, just like a 3. So when I take the partial with respect to x, I'm going to get 3x squared. And then, okay, the derivative of x will be 1, and then I multiply by the constant part, so 3y squared. Derivative of 3x squared is 6x, so I get minus 6x. And now this is just a constant. There's no x to worry about, so the derivative is just 0. Okay, now I've computed the x partial derivative. Now I need to compute the y partial derivative. So let's see here. What do we treat as a constant now? Well, now it's all the x's that we'll treat as a constant. Hey, we can treat the 3's as a constant as well. Okay, so let's see. Derivative of x cubed, well, x is a constant, so the derivative is 0. How about the derivative of y squared? That'll be 2y. And then I multiply by the 3x, which was a constant, so we get 6xy. Okay, well, again, I have just this constant x, so the derivative with respect to y is 0. And then here, the derivative of y squared is 2y. Multiplied by a 3 gives me 6y, and then there's a minus, so minus 6y. Okay, so there's my partial with respect to y. But I need this to be 0, and of course, this is the 0 vector. So when is it equal to 0? Well, I need each individual component to be 0. So I need 0 to equal 3x squared plus 3y squared minus 6x, as well as I need it to equal 6xy minus 6y. And, well, both of these you could see we could do a little division just to make our lives feel a little better. In the top one, I could divide everything by 3. Why not? And I'll get 0 equals x squared plus y squared minus 2x. And on the bottom, I could divide by 6 everywhere, and I'll get 0 equals xy minus y. Well, let's play with this bottom one first, because it looks easier, frankly. I notice I have a y that I could factor out, and I'll be left with an x minus 1. So I now have 0 is equal to a product of two numbers. By the way, notice I didn't divide by y. Unlike these constants, which are definitely not 0, it's possible y does equal 0. And so if I divide by it, I might unintentionally be kicking a puppy. We don't want to do that. So I just factor it out, and I note if I have a product of numbers equaling 0, then one of the two needs to equal 0. And so this says that either y is equal to 0 or x minus 1 is 0, which would mean x is equal to 1. All right, so in order for the second equation to equal 0, there's really only two ways I can do it. Y has to be 0 or x has to equal 1. So then we have this top equation. I'll label that number 1. And I know that if I need both of these to be 0 at the same time, then I'm going to be in one of these two cases, and I just want to plug these into number 1. So let's check the case where y is equal to 0. then number 1 becomes 0 equals x squared. Now there's no y because y is 0, minus 2x. Again, I can factor out an x, and I'll have x times x minus 2 is equal to 0. A product is equaling 0, so I know individually one of them has to be 0. So either x is 0 or x is equal to 2. Okay, on the other hand, it could have been that x was 1. If x is 1, then what happens to equation 1? Becomes 0 equals, well now x is 1, so I get 1 plus y squared minus 2 times 1, so minus 2. And so this becomes y squared minus 1, and that's a great difference of squares, so this is y minus 1 times y plus 1. I again have a product now that equals 0, so one of the two has to be 0. So either y is equal to 1 or y is equal to negative 1. Okay, so let's put this all together. In the case where y is 0, we ended up with 2 different possibilities for critical points. Okay, so critical points of the function f. Okay, we have a set. One of them is when x and y are both 0. So we get 0, 0. We also get when x is 2 and y is 0. So 2, 0. Okay, now the second case where was x is 1, which we haven't handled yet. If x is 1, then y is either 1 or minus 1. So we end up with 1, 1 and 1, minus 1. So in total, we have 4 critical points, right? Recall, critical point is where the gradient is equal to 0, and we ended up with 4 different ways of doing that. All right, going back to our choices, remember one of them was, is it true that f has 3 critical points? Well, no, it has 4 critical points, okay? So this one is going to be false. Okay, it has 4 critical points. Okay, now, the rest of these are all asking whether or not we have things like a local max or a local min at points, and do these match up with what we have? So 1, 1, for example, hey, that was one of our critical points. So this is actually a legitimate thing to ask. 2, 0, was that in there? You betcha, there was 2, 0. Another legitimate thing to ask. How about 1, -1? Hey, there's 1, -1. Absolutely. So all 3 of these are legitimate things to ask. We just need to actually check whether these things happen. Now, in order to check them, we're going to need to use the Hessian of f, right? That comes from our second derivative test. Whoops. All right, so we want to compute the Hessian of f, and you'll recall that the Hessian of f is equal to the partial, or the double partial with respect to x, times the double partial with respect to y, minus the partial with respect, well, it's really a double partial with respect to xy times the double partial with respect to yx. And if we're working in a situation where our second derivatives are continuous, then we know that these are actually equal to each other. Okay, that was a theorem called Clairaut's theorem. So we have Clairaut's theorem. Okay, and since we're dealing with a polynomial, Clairaut's theorem absolutely applies. And so this will be fxx times fyy minus fxy quantity squared. All right, just get 2 copies of that. Okay, well, we can compute this pretty quickly, right? So what do we need? Well, we want to get our partials. So let's get those. So let's see. fx was this function here. So if I take the partial again with respect to x, I'm going to get 6x. Okay, the y part is going to be 0 because we're taking the derivative with respect to x. And then I get a minus 6. So that's our fxx. Okay, now with respect to y. So I go to fy, and I'll take the partial with respect to y. So I get 6x. And, oh, look, minus 6. How nice. It's actually the exact same thing as fxx. Minus, okay, now I go back to fx, and I'll take the partial with respect to y. The first and third components will both be 0 because there's no y's, and the middle one will be a 6y. So I have 6y, and of course I'm squaring it. Okay, and if you didn't believe Clairaut's theorem, of course you could check fy, take the partial with respect to x, and you'll just get 6y. Hey, the same thing we got. Okay. So I'm not going to expand all of this. I'm just going to rewrite it as 6x minus 6 squared minus, and we'll take, say here, 36y squared. Okay. Okay, now what I want to do is evaluate the Hessian at these different critical points. So for example, if we evaluate the Hessian at the critical point 0, 0, okay, when x is 0, I'm going to get negative 6 squared, which is 36, minus, okay, y is 0, I just get minus 0. So that's 36, which is positive. Okay, now the second derivative test says if you have a positive Hessian, then you should check the second derivative at 0, 0. Check that sign. Okay, well the second derivative with respect to x was 6x minus 6. So at 0, 0, that will be negative 6, which is, of course, a negative number. This tells you that in the x direction, your function is concave down, which means you must be getting a local maximum. Okay, so a negative second partial is going to give you concavity in the downward direction, giving you a maximum. Now, that's the good news. The bad news is, if we go back up to the problem, oh, none of them are actually asking about 0, 0. So, okay, we're going to have to check all the other three. Okay, so how about the next one? Let's see, let's jump this back up. How about 2, 0? Okay, well, when x is 2, then we'll get 12 minus 6. 12 minus 6 squared is going to be 36 again. Minus, okay, well, again, the y is 0. So it's actually, again, 36, which is positive. So again, we'll check the second partial derivative. And now we get 12 minus 6, which is 6. Ooh, which is positive. That tells us that in the x direction, we're getting upward concavity, which means we actually have a local minimum. Okay, let's go back up and check what the claim was at 2, 0. It was that we had a local minimum. Hey, that's exactly what we wanted. Cool, so this one is true. All right, let's check the other 2 points, 1, 1 and 1, negative 1. So if we check at, say, 1, 1, now our Hessian, okay, when x is 1, we're going to get 6 minus 6, that's 0. Okay, that goes away. So 0 minus, and now when y is 1, we'll get minus 36, which is, well, that's, of course, negative 36. That's a negative number. Beautiful thing about the second derivative test is when you get a negative Hessian, you're done. You know you have a saddle point. So we're going to get a saddle point at 1, 1. All right, let's check. Something said saddle point. Ooh, it said it at 1, negative 1. Yeah, we don't get a local maximum at 1, 1. So this one is false. All right, let's check 1, negative 1 then. So 1, negative 1. Let's see. Well, do you notice here the y can't tell whether you put in a positive or a negative, and we didn't test, I mean, we didn't change the x value. So this also has to be negative 36, which is negative. And so we really will get a saddle point also at 1, negative 1. Okay, and that actually was the last claim. So this one, f does have a saddle point at 1, negative 1. So this guy is actually true. All right, well, it's been an incredible journey. We'll see you with some more math later that's not on the super quiz.